So this is the problem we're solving. At t equals 0, a star of mass 4 times 10 to the 30 kilograms has a velocity of 7 times 10 to the 4th, 6 times 10 to the 4th, negative 8 times 10 to the 4th meters per second, and is located at 2 times 10 to the 12th, negative 5 times 10 to the 12th, 4 times 10 to the 12th meters. Relative to a center of a cluster of stars, there's only one nearby star that exerts a significant force on the first star. The mass of the second star is 3 times 10 to the 30 kilograms. Its velocity is 2 times 10 to the 4th, negative 1 times 10 to the 4th, 9 times 10 to the 4th meters per second, and this second star is located at 2.03 times 10 to the 12th, negative 4.94 times 10 to the 12th, 3.95 times 10 to the 12th meters, relative to the center of the cluster of stars. And we are going to be solving A and C. And A says at t equals 1 times 10 to the 5th seconds, what is the approximate momentum of the first star? And C asks at t equals 1 times 10 to the 5th seconds, what is the approximate position of the first star? So, we have the values for star 1 written down and the values for star 2. And we want to find the momentum of the first star at t equals 1 times 10 to the 5th seconds. So, for our momentum principle, we can use this formula. Our final momentum is going to be the initial momentum plus F net delta t. And we are given the mass and the velocity of the first star. Therefore, we can say that the initial momentum is just mass times velocity, and those are the same thing. So we know mass, we know velocity, we know delta t is 1.5 seconds from the question, or 1 times 10 to the 5th seconds from the question, and we need F net. And F net is negative g times m1 times m2 times the unit vector all over the magnitude of the vector squared. So we need r, essentially. We need the vector of r, that is the position between the first and second star. We need the magnitude, and we need the unit vector. So first we're going to get the position, or the distance between the two stars. That's the vector we're trying to get. So to get that, we're going to subtract the position of the second star from the position of the first star. So here we have the position of the second star minus the position of the first star, and that gives us this: 3 times 10 to the 10th, 6 times 10 to the 10th, negative 5 times 10 to the 10th meters. Now we want to find the magnitude of that. So we're going to square root and square, respectively, and that gives us the magnitude, which is square root of 70 times 10 to the 10th meters. Now we want the unit vector, which is going to be the normal vector all over the magnitude of the vector, and that is going to give us this: 3 over square root of 70, 6 over square root of 70, and negative 5 over square root of 70. So now we want to plug this in to find F net. So we multiply negative g, the mass of the first star, which is 4 times 10 to the 30, the mass of the second star, the unit vector, all over the magnitude of the vector squared, and that gives us this. Now we can plug F net into our momentum formula. So we use the mass of the first star, which is this, the velocity the first star has, and then we add F net, which is what we just solved for right here, delta t, which is just 1 times 10 to the 5th, so 10 to the 5th. And that's going to give us this. And this is in kilogram meters per second. Part C asks for the position of the first star. So we know the position update formula is R2 equals R1 plus velocity times delta t. So we know R1, the position of the first star. We know the velocity of the first star, delta t. We just plug in, and we are given this. And that is how you solve number 30.